Hi everybody, my name is Britt, and today I want to try to answer the question, what is graph theory? Very often, my friends and family will ask me what I study in school, and when I say graph theory, they respond with this. So this video is meant as a sort of introduction to the field, which is hopefully accessible to everyone. Now, what I don't want to do is flash a complicated definition on screen and try to slowly parse our way through it. Instead, I'd like to start with a problem. Imagine we have three houses along a street, and across the street we have a water supply, an electric plant, and a source of gas for our homes. Of course, each home needs to be connected to each utility, and our question is it possible to arrange these utility lines so that none of them cross? Now, an important observation is that it's unimportant that these are houses or that these are utilities. That's just context for the real problem. In our picture, they may as well be dots. And that simplification leads me to the definition of a graph. A graph is made up of two things, a set of objects called vertices, and the connections between them called edges. They're very simple. Some objects and the connections between them, or in our language, a set of vertices and the edges between them. Now let's get back to our question, which we can now translate to ask if we can draw this graph so that no two edges cross. Let's give it a try. Maybe we start with these horizontal edges and then draw some diagonals like this. Now our lines will have to curve behind the houses, which is fine, and I think we can fit one more in there like this. But now we have a problem. No matter how we try, we can't connect these two vertices without crossing some other edge. Now, that was just one attempt, and maybe a different technique would be smarter, but I can actually tell you the answer is no. No matter how you try to do this, there will always be at least one crossing of edges. And the reason, in my language, is that K33 is not planar, where K33 is the name of the graph we've drawn, and planar means that you can draw the graph without edge crossings. For our next example, I want to look at the bridges of Konigsberg. Konigsberg is a city which, in the 1730s, was in Prussia, and it looks something like what we see in this picture. Now, I know it's a bit unclear, so maybe we can add some color, and that's a bit better. The city is actually separated into four distinct landmasses by a river, and it contains 7 bridges, in red, connecting these regions of land. And the question that became popular around the city was, is it possible to take a walk through the city so that we cross every bridge exactly once? It doesn't matter where you start or end. It only matters that you cross every bridge, and that once you cross a bridge, you don't step foot on it again. Now, naturally, I want a graph to represent this situation, and since the bridges seem like obvious connections, or edges to me, let's make our land masses into vertices. So we can represent this northern region with this red vertex, the left island with this blue one, the bottom left by this yellow vertex, and our last one with green. Then, since our red and blue chunks of land are connected by 2 bridges, we'll draw 2 edges between those vertices. And since the red and green land masses are connected by just 1 bridge, we'll put just 1 edge there, and so on, to create this graph. And just like we did before, we can translate our original question into a question about this graph. Can we traverse the edges of this graph so that each edge is used exactly once? Once again, let's give it a try. So here we are, and let's say that we start up in the red region. And we can travel down and right back up, and then maybe to the right, back over to the blue island, down to the yellow, over to the green, and now we're trapped on the green island, and we've missed a bridge. So once again, the answer to both of our questions is no. And this time, the reason is that this graph does not admit an Eulerian trail, where trail means you don't reuse a bridge, and Eulerian means you use every bridge. By the way, that adjective comes from Leonhard Euler, who actually invented formal graph theory just to solve this problem. He also did a ton of other stuff that earns him my vote for the greatest mathematician of all time. Okay, time for one last example. Here is a map of the United States, and I want to point a few things out. First, as with every other map we might see, any 2 regions that border each other, or states in our case, are colored differently. Not doing that would just look terrible. And I also want to highlight the fact that we've only used 4 colors here. This nice pastel palette of green, purple, pink, and yellow. So this is a map. Where's our graph? Well, our states are going to be our vertices, and our connections are going to be something we've mentioned already, borders. So any 2 states that share a land border will have their corresponding vertices connected by an edge. So now we've got this nice, vaguely US-shaped graph, and I'll just tweak it a bit to make it more readable for us. That's better. Before we go further, I want to re-emphasize something I've already said, but in graph terms. This graph is properly vertex colored. Now, vertex colored is kind of self-explanatory, but what do we mean by properly? That just means that 2 vertices of the same color are not connected. Or, in other words, the opposite ends of every edge are different colors. So this is just representing the fact that our map wasn't colored all janky, with bordering states receiving the same color. Now I want to shift my attention to this small section of our graph, which corresponds to the state of Nevada and the 5 states bordering it. And what I want to try to do is to color this graph with just 3 colors instead of 4. So we'll have to start somewhere. Maybe we make California green. Then, since it borders Arizona, that will need a different color, say purple. Of course, the choice of colors here doesn't matter. Now, Nevada, since it borders both of these states, will have to receive a color different from both of them, say red. But by that same sort of triangle logic, Utah will be forced to be green, and similarly, Idaho will absolutely have to be purple. But here we have a problem. We've done the best we can do, but our last vertex, Oregon, borders 3 other vertices which all have different colors, and so it will have to receive a 4th color. By the way, a graph like this is called a wheel, which seems appropriate, and since there are 5 sort of spokes and 5 rim edges, we would call this W5. Anyways, what we just proved is that our US graph requires 4 colors, which means that some sort of 3-color theorem just isn't going to work. But what will work, and which is kind of astoundingly true, is the 4-color theorem. Every planar graph can be properly vertex colored with just 4 colors. No matter how convoluted you try to draw a graph or a map, as long as no edges cross, you can color it like I have with only 4 colors, and you'll never need a 5th. And that is all I have for y'all today. We talked about the non-planarity of K33, we looked at the very first graph theory problem in Konigsberg, and we ended with the very famous 4-color theorem. And I'd just like to end with a reminder that if things ever seem like a jumbled mess, a new perspective can make them clear again. Thank you.